Okay, I'm going to be going over how to do the steps for the Xfoil project. I have it pulled up on another monitor, so we'll just be going through it. So first part of the project asks for the two NACA airfoils, first one being 0015 NACA airfoil. So just go ahead and enter that, and it should pull up all the data, as we can see here. And then we can do the pan to go ahead and smooth out any rough edges, and then PPAR to check out the actual airfoil, which is right there. And then what we're going to do is we're also going to change the panel nodes. So hit N, and then how many panel nodes we want. So 250 for this case. And then we're also going to change the panel density ratio. So T and then 1, so it's the same on the front as it is to the back, as you can see. And then panel nodes 250. And then keep hitting enter till we get out of that. And now we're back in Xfoil. So to go ahead and get the actual process iteration, to go and hit OPER for operations, and then the I next to operations indicates that it's in viscid flow. So to change it, we can go ahead and put visc, and then it's going to ask us for the Reynolds number, and for this one we're going to do 1,000,000. So 2, 3, 4, 5, 6. Enter. And then now it changes our Reynolds number to 1,000,000. And then we go ahead and do a sequence. And this is from -5 to 15 in increments of 1. And this is for the alpha. That's why there's an A in front of the sequence. And then you should run it, and it should go ahead and give us our data here. Now to go ahead and to actually write it to a file, so do pack, so PACC. It's going to ask us for the name. So we're going to go ahead and do, I guess we'll call it NACA 0015. This is what we're doing. Hit enter again, and then we can go ahead and do the same thing. So -5 to 15 increments of 1, and then boom, it should do it. And then it'll actually make a folder for it right here. So NACA right there. And then so that's it. And we can actually go ahead and take a peek at this. No pen, and you can see it gives us our numbers here. You can see the -4 and 5 are not there as long as it's 15, and that means that it wasn't able to converge for those alphas. But we can use the rest of the data, which is fine. Now to go ahead and open it in Excel, you simply just open it up. So browse, and then the same spot, all files, and then it'll go ahead and give us this prompt to import a text file. Hit finish, and then here we have all the data. So then going again through that, so what I'm going to do is I'm going to actually go ahead and close Xfoil out, that way to kind of refresh it. And then now we're going to do the NACA 2415. And same thing, so pane, and then PPAR. Go ahead and open it up. And then we're going to change the panel nodes to the same number, so 250. And then the ratio is back to 1. So everything is the same, the trailing edge to the leading edge. And then same thing, op, and then visc, and then Reynolds number of 1, 2, 3, 4, 5, 6. And then we can go ahead and do pack from the get-go. And then we're going to call this one NACA 2415. And same thing, and then we can do the A sequence, -5 to 15, increment of 1. And there it goes. And nice and neat. Go back to our folder, and we can see that we got the new NACA 2415. Here you can see all the alphas actually converge in this one, so that's nice. And then it's the same process to open it up. So file, open, and then browse NACA 2415. Same process, next, and finish. And here's our NACA 2415, Reynolds number of 1 million. And here's our other values. So it's the same thing again, and then we're going to do this time for the Clark value. For the actual Clark value, I actually got the text file from the database, the UIUC database, and went ahead and changed it as Xfoil won't recognize the format it was in. So I went ahead and changed it from starting from the leading edge, going on the top, or from the trailing edge, going on top to the leading edge, and then from the leading edge going on the bottom to the trailing edge. And so that's what I did here, some manipulation of the actual numbers. And then it's the same thing. Now, instead of actually typing in which airfoil we want, we're actually going to load, and then the name of the file with the txt on the end there. Since mine is a txt file, so Clark W and then text document. So hit enter, and then we can give it the name. I'm just going to name it Clark W since that's what it is, and then we get our Clark W airfoil there. So it tells us here that we have port input coordinate system. So we're going to go ahead and pane first, kind of smooth out some of the rough edges. And then we're going to do panel nodes. So N250 again. Or actually, we got to do PPAR first. So PPAR to get into the actual setting. And then now we can go ahead. As you can see here, the number of panel nodes is 160 to begin with. And the panel ratio, density ratio is 0.15. So you can see it's a bit different, more heavy nodes here in the leading edge compared to the trailing edge, and that's what we're changing. So nodes we're going to change to 250, and then the ratio density, or density ratio, we're going to change it to 1. And then you can see now there's the same amount of density panel nodes to the leading edge as it is to the trailing edge. So go ahead, done there. And then it's the same steps as we did for the other two, for the NACAs. Reynolds number of 1 million. And then we can go ahead and do PPAC again. And then this one we're going to call Clark W, as it's the Clark W. And then we can go do the A sequence from -5 to 15 is our range of alphas we want. And we're going to do them increments of 1. Go ahead, enter, and it'll do it here for us. Coming back, now we have our actual Clark W file. And we open up a notepad, and we can see got all the values. And then we can actually go ahead and open it up. Clark W, right? Just in the same steps as before, next, finish. And then here's our Clark W, Reynolds number of 1 million. I actually do have all of it already completed, so I went ahead and made sure I could complete it first before making the actual video. So open it up here. Here are the same NACA 214 and then the Clark with the million. And then as the assignment indicates, it wants us to go ahead and then graph it within Excel. And so this is the lift coefficient versus the alpha. the drag coefficient versus the alpha. So alpha on the x axis, and then the drag coefficient on the y-axis. And then the aerodynamic performance, which is CL over CD. So the lift coefficient over the drag coefficient versus the alpha. And that is that. So that completes the first part. So I'm gonna go ahead and close this and open it up so we kind of refresh. And then now we're gonna do part 2, which is the different types of flow for the Clark W. So we're gonna go ahead and load in our Clark W. So we're going to go ahead and open up our Clark W. I went ahead and deleted that, and I have the results in here. Clark W results there. So go ahead and move that in there, and then that's fine. I'll do it later. So then I'm going to go ahead and load in our Clark W, and we're going to call it Clark W, and there she is. And we're going to go ahead and pane, and then PPAR to go ahead and change the nodes, so 250, and then the density ratio 1. So you change it there, and that's it for that one. We'll go ahead and operations. And then the first part of part 2 is with inviscid flow. So we'll keep it here, and we'll do the same thing. So PPAC, and we'll call it Clark W to denote which we're doing here. And then it's the same thing. So A sequence, so alpha sequence from -5 alpha to 15 alpha in increments of 1. Go ahead and enter. And there she is. So -5 is 15. Come back here. We have our, and boom. So there's that. I'm going to go ahead and do the next 2 without showing the actual file. So I'm going to go ahead and close this out and do it all over again to make sure that we don't have any lingering data in there to mess up any of our simulations. And Clark W. R and 250 T1, and then operations. And now for the second part of part 2, it's asking us to do for viscous laminar flow at a Reynolds number of 300,000. So I'm gonna go ahead and put viscous and a Reynolds number of 300,000, and then PACC again, so PAC, give it the name, so Clark W laminar. And then we're going to go a sequence, -5 to 15, increment of 1. I'm going to include the space there. And then, as we can see here, I think some of them actually didn't converge, but it's fine though. So we're gonna go ahead and do the same thing again. So load Clark W dot txt. W. And then we're gonna pane and PPAR and 250 T1. Now for the third and final part of part 2, it's asking for a Reynolds number of 1 million. And then it's the same thing. PPAC name, we'll call it RW turbulent. And then a sequence, -5 to 15, increment of 1. As you can see here, it's going to go ahead and through this. I'm going to show for a CP here. And then as you can see here, we got inviscid, turbulent, and viscous, turbulent, and laminar flow. So for part 2, I have them here. So in viscid flow, you see the CD is 0, so drag coefficient is 0, which is expected. Here's the viscous laminar with the 300,000 Reynolds number, and then the turbulent with the 1 million, which is the same as one in the part 1. Then we can actually look at the graphs. And it's the same graph. So CL versus alpha, CD versus alpha, and then the aerodynamic performance. And then I also got the max lift coefficient or the minimum CD coefficient, and then the maximum aerodynamic performance at set alphas. Like I said, for the inviscid flow, you see that there's the minimum CD is 0 because there is no CD. It is supposed to be 0, and so therefore our aerodynamic performance will be divisible by 0, so it is undefined. And that is part 2 of the assignment. And now for part 3, which is the flaps. So we'll go ahead and load in our Clark W text file again to get our airfoil. Just move this to the side. Go ahead and paint first and PPAR. 250. T1. And that's that. And then now we're going to actually, so for part 3, it's asking for the million Reynolds number again. So we already have that data twice. I'm just going to show how to add the flaps. Geometry design, so GDES, and it's going to say now we're working with it. And to add a flap, go ahead and type in flap. It's going to ask us where we want the hinge location, and we're going to put it right here at the 0.7. So we're going to write in 0.7. And then the Y location, we're going to specify by the thickness. We're going to go half. So we type in 999 to get the thickness, and then so 0.5, so half the thickness. And then now it's going to ask us for the degrees. So we're going to go ahead and put 10 degrees, and positive is downward, so we want it to go downward. And then you can see here it's showing us how it would look. Now to go ahead and complete it, to actually have it, you got to execute it. So EXEC, and then we are done. So now we're going to go ahead and PPAR again, because as you see, the number of panel nodes is 35. So we're going to go ahead and change that, and we're going to go into 50 and T1 again. And then we're going to do operations at that million Reynolds number. We'll actually write it down this time. PAG, we'll call it Clark W10 for 10 degree flap. And then a sequence from -5 to 15 to 1. Okay. And then we're going to close it and do it all over again for the for the 20 degree flap. So same steps as before, just gonna go ahead and do that, and then GDES or geometry design, and we're gonna add a flap, and that flap is gonna be the same location, so 0.7, and then we're gonna do it at half the thickness, so 0.5, and then we're gonna go 20 degrees instead of 10 this time. And since that's what we want, we're gonna go ahead and execute. And then we're going to do PPAR again. And when we P-part this time, you can actually see the 20-degree flap there. So we're gonna go ahead and do the same thing, 250, T1. And then coming back, you see panel nodes, 250, still got that nice flap there. And then it's the same thing, operations, viscous, the random number, PPAC, and we're gonna call this Clark W20. And then a sequence from -5 alpha to 15 alpha, increments of 1 alpha. So it did not converge, so I'm just gonna go ahead and try it again. This happened when I was doing it earlier, and now for some reason it goes all the way through. And so that is done for the Xfoil. So now we're gonna come back. So we have all of our data in here, which I already have. Like I said, we already have the viscous turbulent of no flap from the other part, and then this is with 10 degrees. You can see right here, Reynolds number of million, so it's still the same thing. And this one goes from -5 all the way down to 15, which is nice. And this one actually misses a few in between, and that's okay, but we still got plenty of points. And so when we come to graph it, you can see that gap and jump with the missed points there, but same graphs, lift coefficient versus alpha, drag coefficient versus alpha, and then the aerodynamic performance at every alpha. And same thing with the table, found the max lift coefficient, the minimum drag coefficient, and then the maximum aerodynamic performance at each. So yeah, and then that is it. So I went ahead and posted on a thing, on a Word document to submit, and that is it. That is my my project. That's how you do the Xfoil project. Sweet. Thank you.